Okay, great. Hope everyone can hear me. Um, cool. Let's get started. First of all, thanks everyone for the opportunity to share some of the work that we have been doing at Clary. If for those of you who know what embeddings are, you'll have a fair sense of where this is going. But in case you don't, I've put in enough efforts to make sure this talk is self-contained, as self-contained as possible for an engineer. Um, I mean, this is a big screen. Usually shows something very entertaining. Hopefully, mine is interesting. Um, what what I want to focus on today is that when you use embeddings and prototyping, you can get a varied amount of performance, right? They can be lackluster, or they can be excellent at semantics, depending on where and how you fit them in, right? So if you don't understand, but embeddings, I'll still cover them, right? What I want to do today is make the case for customization as a way for improving your embedding performance, right? So, and I'm not just saying, hey, you can customize embeddings. My goal is to show you how low-hanging of a fruit that can be when you want to use them within your pipelines, right? And your product, primarily. My name is Srikar. I'm an architect at Clary. In my previous life, I was the founder and CTO of a company called Wingman, currently called Copilot, was acquired by Clary a couple years ago. That's started my journey with Clary. And much of this talk is actually rooted in the context of the product we are trying to build. So I want to take some time to tell you a bit about what Clary does and what Copilot is, because that's kind of essential for you to follow along with the work that we have done and how that fits into the user experience and all of that. Cool. So let's get started. So what is Clary? Clary is a SaaS platform for revenue teams to collaborate on revenue processes, right? So if you're the engineer that, like I am, I mean, I never connected, why do you need sales with software, right? So sales was for something else. Good software doesn't need to be sold. So I couldn't be more wrong. Selling is not just while it's an art, Clary stems from the premise that it's more of a process. There is a method to this madness, and it's an important function in the company that spans across multiple teams, right? You have the CRO, whose job is to, who's trying to answer the question, am I going to meet or beat or miss revenue expectations this next quarter, all the way up to the sales manager, hey, can I meet my quota? Or marketing, can I get enough of pipeline, right? So there are like at least 5 teams that I can name here. So like sales managers have a different goal. Their job is to ensure that they look at the deals, provide enough coaching, manage them on a deal-by-deal basis. Whereas marketing is concerned purely about how do I increase top of funnel? How do I get enough prospects into my pipeline so that my sales team can convert them into happy paying customers? Customer success is, hey, one deals are way more important. Make sure you save revenue, make sure people get value from your product. And finance is making sure the numbers add up properly. So while an important function like revenue, it's not unusual for an important function like revenue to have so many teams coordinating to achieve the goal. The problem before Clary was that they weren't working on the same set of tools, right? So imagine you have 2 teams trying to build the same product but are building on 2 different Git branches, right? That's the equivalent of what was happening here. So Clary was the software, the suite that brought all these teams together, helped them align on one common set of data and drive revenue, right? So there are still a couple of important phrases here that I need to unpack for an engineer, right? So revenue teams refer to these 5 teams that I laid out here, and revenue processes are a whole different thing, right? So just like how we as engineers, we have a whole bunch of processes to make sure that we can run really large engineering teams, right? So you have planning, you have code reviews, you have you have the things that you're forced to do on Jira, right? So you have all sorts of things. Similarly, revenue teams have their own processes, right? So at different cadences, there are things that they do daily. That is, They have to capture CRM data. They have to do follow-ups. They have to look at their schedules. They have things that they do weekly. They have to provide weekly coaching, roll up deal inspections, things that you do quarterly business review, planning, yearly. Again, you have your sales kickoffs where you plan for the year, where the company intends to be from a revenue perspective, how they need to manage pipeline, all of that, right? So what this has to also align with what product will get built, all of this. So Clari is a software that helps both revenue teams integrate and run their revenue process on one set of software, right? CRM, usually people think of CRM as that piece of software, but actually revenue teams are using much more than CRM. So Clari Copilot is a part of the Clari suite of products, which is trying to extract unstructured information from sales calls, right? So these are calls which are recorded on platforms like Zoom, and the whole premise is that audio is just inherently time-consuming to analyze manually. So there is a lot of data hidden there, which is why most people don't do anything with it. They just record it, probably for compliance. And Copilot was born out of the need for unlocking this data, right? So there's so much you can learn from what conversations your sales teams are having with your prospects. So the way Copilot does this is by recording, transcribing, and analyzing these conversations, right? And much of this analysis happens through applications of some form of natural language processing over these transcripts. Before, say, 2017 or 18, NLP meant so many other things, right? So some LDAs, lots of things, right? Clustering, all those things. But today, it's almost unequivocally some form of application of LLMs. There are so many things that you do with LLMs on transcripts to unlock this data from sales conversations. Let me show you a product screen. I'm so thankful for this large screen, which will help you actually gather all the detail from this. So this is an important part of the Copilot product, right? Where you're trying to break down a single call. So there's a lot going on here, right? So there is data from the CRM on the left, where what is this call related to, right? This call is related to a specific deal, and it has some metadata associated with it. And then the transcript as well as the player are front and center. So you can actually go through the entire transcript. A lot of the analysis is actually happening on the right. So you have what is called a summary, where somebody doesn't want to look at the entire call, but wants to know what's going on. Then there are in each of those tabs contains some extract through an LLM to understand what questions were asked, if there were any objections, things like that, right? Now, it's not so hard to imagine a use case for like LLMs or LLMs here, right? So let me give you a few examples. For example, I want to know what kind of patterns happen in my calls, right? What's a pattern is like an objection happening in the call, right? Well, can you show me all the objections happening in the call? To be able to answer questions like this, you need to have some technology which can take two pieces of text and say if they are actually similar or not, semantically, right? Now, this is exactly where we start getting into the technical stuff, that is embeddings, right? What embeddings are trying to solve. Now, let's start with the problem and try to work on this from first principles. So how do you say if two pieces of text are similar? The most naive way to do this is string compare, right? And it has its obvious drawbacks, which is, unless you say the same thing the exact same way and the transcription catches it the exact same way, you're never going to match them, which means you're never going to see any patterns. Every string seems unique. OK, so we can break it down into atoms, which are the words in this case, and try to compare two strings as which of them have more similar words. While this is a lot of progress, it has its own drawbacks, right? So you have a lot of irrelevant words. You'll have a lot of bias towards longer pieces of text. I mean, all of this is incremental progress that we have achieved in the NLP community over like years, decades, right? So removing the uninformative words, paying attention to the informative words. How do you recognize informative words, right? Those which are not occurring everywhere, but only specific to your documents or a small set of documents. You try to use a mathematical function to assign importance. And that's what I'm trying to describe is what the TF-IDF process that was industry standard, is industry standard to compare two pieces, to represent a text, right, semantically. This is another way to look at TF-IDF, right? Let's say your dictionary is composed of 5 words. To draw focus away from the what specific words, so I've represented them as 5 colors, right? Actually, this is not my. I've linked the source, but this is not my diagram. So you have 5 documents. Now you have a score for how much does that word represent your document. What TF-IDF tries to show you is if 2 documents have similar looking vectors, that means they're talking about the same thing. And if you look, each column is a term and each row is a document. So if you look at any column which has all zeros, which means that term is not very useful in describing a document, right? Any column which has just a few numbers, it's actually discriminating between 2 different kinds of documents, right? So look at the second column over here. Similarly, when you go to rows, 2 rows which have similar looking numbers means that they are the exact same, they are talking about something similar. So all this muckery got us really far, right? And this is the basis for search engines. This is the basis for many things which are still the state of the art today. And this is like lexical similarity is not to be underestimated, right? It still forms a very strong baseline for how good can you do to retrieve a document through search, right? So it's still, even today, when you try to build some retrieval system, your first will be through Elasticsearch or something, which is all lexical, and they're still a very strong baseline. To understand why what embeddings solve over this, it's useful to see where a system like this fails, right? Like take 2 sentences. How old are you and what's your age? Now you try to build a similar representation for each of this. It's not going to do very well because these 2 statements, while they semantically mean the same thing, they really don't share any words, right? They don't have any common words. That's the problem that embeddings try to solve. And the genius of the solution actually comes from trying to actually do this with words, not with sentences, right? Here we are trying to do this with whole sentences, but the solution comes from like a Google engineer. I don't know the exact year, maybe somewhere in 2012 or 2011. He said, the right data structure for a word is like a list of floating point numbers, right? So I'll take a list. And you can treat this list as if it's a list of size, it's a fixed length list, right? So each word has the same size list. And you treat each of these lists as a point in an n-dimensional space, where n is the size of the list. If I can learn these numbers such that 2 points which are close to each other mean the same thing, and 2 words which are farther from each other mean something very different. And he went further, right? So I can do they're also conducive to mathematical operations. For example, there is king and queen. So if you remove man from king and add woman, it's closer to queen, right? So you can actually do math on these vectors, right? While this was a very innovative idea, in my mind, the genius was not in the whole idea of the data structure to represent a word like this. The genius was in how these things were learned, right? He found a way to actually learn these just through like tons and terabytes of unstructured data which was lying free on the internet, right? The postulate was that words can be defined by the company they keep, right? So When, how do you complete a sentence? A word is defined by all the words which occur around it. If you can replace synonyms with synonyms in the same context, they mean the same thing. So I can learn about a word by all the other words around it. So essentially, sentence completion, that's the task through which he learned these word vectors. And they were fundamental, right? They were fundamental to everything we have achieved today with LLMs, right? And soon somebody said, if this works with words, why doesn't it work with sentences? And that's how sentence embeddings came. While sentence embeddings are also learned in a similar manner, there are some very fundamental differences between learning sentence embeddings and word embeddings. I mean, we won't get into that, but all I want to say is, at some point, we arrived on using a list of fixed length floating point numbers, right? It does not depend on the length of the sentence. You have a sentence with 100 words, you have a sentence with 1,000 words or 10 words. They all they are all represented by a fixed length of floating point numbers. And these numbers, if you compare the numbers for two different sentences, and the distance between them will tell you how similar they are, right? These are exactly what text embeddings are. Today, LLM APIs like OpenAI, Claude, lots of open source LLMs, lots of them will give you, they'll have an embedding API. You can pass in text and get these vectors out. You can store them in a database. You can try to do retrieval on this database of just embeddings, right? Without looking at anything else, you can just retrieve using that and try to build products around it. So this is where we started. So here is another example. This image is from Google, Universal Sentence Encoder, right? If you see the two examples that I used, how old are you and what's your age, they're also used here, and you can see how embeddings actually solve for that use case. So I have a list of 11 sentences, right? So you're comparing these 11 to each other, and you have the scale on the right, which shows you the strength of comparison. Closer to a dark red means that the embeddings thing, comparing the two embeddings, tells you that there is a very strong similarity. And the lighter the color gets, which means that they're not too similar. As you can see, the top three sentences on the right, so the diagonal will always be, the diagonal is always a sentence being compared to itself, so you expect it to be very dark, right? If you look at the first three sentences, I like my phone, the phone is not good, cell phone looks great. While they are not saying the exact same thing, they're talking about a phone, and they should have a very strong head, which they do according to embeddings. If you look at the next two ones, which are the most interesting here, right? Will it snow? So not the next two ones. Let's say recently a lot of hurricanes have hit the US and global warming is real. They look like they're talking about some climate change kind of thing, right? And if you see, as this is pretty hard, but embeddings actually are able to highlight a stronger match with both of these things. And the example that I used in the previous slide, how old are you and what's your age? Embeddings think they're exactly talking about the same thing, right? Irrespective of them not sharing a single word. So these can be very powerful when used in your product, in my opinion, in conjunction with lexical methods, lexical methods, right? So I told you a little bit about the Copilot product. It's not so hard to imagine, how LLMs fit within the Copilot product, right? So there are cases where these embeddings are very implicit, in the sense you take a transcript and you ask an LLM to summarize it. You never see an embedding or a list of numbers or anything anywhere. Text in, text out, right? Very simple. Where like you give it a piece of text and can you tell me what the customer's sentiment was? Was he angry? Was he excited about the product? Do you think he was not very convinced? Again, text in, decision out, right? Whereas, let's say you want to search through your calls and you want to find something relevant, right? Most LLMs today the unit of currency is token, right? So because that also defines the computational complexity. So in terms of number of tokens you have to attend to and things like that. So because of this, context length is limited. So you can't pass your entire repository to your LLM and ask questions. So because of which you need to do some form of retrieval, right? And retrieval is where LLMs are good at. You need to find something relevant to what you're asking. That means that you need to be able to seek for that information in a semantic sense, and that's exactly what embeddings let you do, right? So they help with search, they help you chat with your data, they help you do topic discovery, what patterns occur in my calls. Those are the kind of things where Copilot has a very natural use case for embeddings, right? Again, to drive the point about where they are very explicit and implicit. Again, here is like a Slack integration that Copilot has, where after every call we send not the prospect but the salesperson a summary of the call so that they can share this with the prospect. So here you can see like a smart summary which is basically sending the call and getting a summary. Or you have some content in HighSpot or some other marketing store. You want to be able to use this content and use this as material for training your reps real time, right? So that's where battle cards are. Most people don't adopt this because it's very hard to create that very short form content. LLMs can do this for them. Another part of the product is let's say I'm running my sales team, right? So my team is talking to prospects, and my competitor gets mentioned. That is very interesting data for me. I want to know what people are talking about my competitor in my calls, right? But I cannot, if I have a large enough sales team, it's just not technically tractable for me to do it at scale. Now, a good way to do this is you can get an LLM to bucket this for you. But to do this, you can't just throw in all the data and ask it to use a concrete mixer approach here, right? So you want to be able to do some form of binning, clustering, and all of that, and that's where LLMs are really powerful here. So fine. So as I said, there are APIs. OpenAI provides APIs. There are many models, right? Why do you need customization? So in 2018, that's right around the time where BERT came out. And I think based on BERT, Google had this universal sentence encoder that they published in TensorFlow, TF Hub. So we built semantically similar phrases using that. Never picked up as a product. People never used it. We always thought of it as this is a setup issue. Some people don't set it up. Large teams will do this. Never worked out that way, right? In 2022, product real estate is very expensive, so you wanted to remove parts of the product to make space for much better product, right? So this is a very strong statement coming from product team to remove an existing thing, which means it shows it just wasn't working. There is also intuition, right? So these LLMs are like billions of parameters, right? Tens of billions. The small ones are like about 10 billion. The large ones can be hundreds of billions. Now, they're trying to learn two things at the same time. They're trying to learn English as a language, as well as the specifics of a particular domain, right? Sales. Now, customization is trying to separate those two, tease those two apart. See, once I have a model which knows what English looks like, I can get that model to learn the intricacies of my domain better. It could be medical, it could be sales, it could be whatever, right? There is some intuition behind this. So customization is trying to do that part separately. So there are a couple ways we can customize, right? So most people, when they think about customization, they think about taking a prompt and customizing the prompt and get their customization baked into the prompt. That's the lowest hanging fruit. Then they go to RAG. RAG is basically saying, can I have a very large context of things? Can I fetch the context? Can I give a model which knows how to reason from something and set the basis for what to reason from using the context that I retrieve, right? That's another way to do it. Fine-tuning your model itself is a great way to do this, but usually not possible because there are a lot of great performing closed source LLMs, right? OpenAI, for example. You don't get access to the workings of the model to be able to fine-tune it for your own task. So, but there are still ways in which you can do this. So you can break down customization. There are like 4 different parts, right? So you need to decide on some architecture. You need to pick a particular task. you need to pick a data set, you need to pick a metric. How do you evaluate this? So let's say there's an architecture, right? So X is the embeddings that I'm getting, and I will learn a new matrix W so that when I multiply it with that, I'll get a new set of embeddings Q, right? That is one way. Why would I do it this way? Because of closed source models like OpenAI. Now, I don't have access to the model, so I can't fine-tune the internals, but I can learn some projection of those things so that I can get these embeddings to do better, right? Of course, this is not the most ideal scenario, but if you're working with really good vectors already, this is one way to do this. This is not my original idea. This is actually from the OpenAI cookbook where someone built a code search tool using this kind of projection very, very well, right? So that's where it came from. The other one is the more obvious one. If you have an open source model, like what Facebook is doing for us today, you can pick one of those models and you can just fine tune it for your own use case. Of course, it needs a lot of specialization. You really need to know what you're doing, but that's still a way to do it, right? There are roughly two different ways for architecture. Now, coming to the task, again, there are the kind of tasks that apply to the Copilot world are two kinds. One is a search use case. Given a repository and a query, I need to retrieve something. Or given two pieces of text, I need to build a metric of similarity. You can build over this, right? You can build clustering over this. You can build so many things over this. They are very, very, very different, tasks. It seems like, on the surface, it seems like searching for something is finding something similar to your query, right? It's actually not. I'll show you in a second why, right? It took me a while to actually realize that. These are very two different looking tasks, produce very different forms of embeddings that you need to use carefully. So take this example, right? So if you search through your repository for, hey, what were the key objections raised by the customer, right? One of the valid responses for that is, hey, I think your product is priced too high, or I don't have the budget for it, or something like that. They're not two similar looking sentences. Whereas in the similarity world, I'm trying to identify, hey, your product is too expensive, and we do not have the budget for this, as something more similar looking, right? So I hope this is clear. So the thing with search is, to this day, right? So you want to look for something. Mentally, you're working backwards into, hey, what is the kind of query that would capture this? You're really not talking to a system or a repository, but you're actually trying to figure out the keywords and try to look for those keywords specifically, right? So, but that is changing today with a lot of people using Perplexity and using OpenAI, ChatGPT, Gemini for their as a replacement to search. Search as a product is actually changing today, right? Okay, coming to data set. So an important component of customization is building your data set. You need this data set not just for customizing, but you also need to evaluate and see if you did any better than where you were before. So we said, okay, Copilot has a chat functionality. Let's go look at the logs. Let's get what are people searching for in Copilot. Turns out they're all very navigational, right? So on the right is, when in 2014 or 15, or maybe it was 2011, when I used to work at Google, there was a statistic which blew my mind. The most popular query on Google was Facebook. So that was a way for people to get to Facebook. They would actually Google Facebook and click on the "I'm feeling lucky" button or the first search result, and that was a way to get to it, right? So those are called navigational queries. Google takes them very seriously. Lots of search advertising dollars go to the search queries. Turns out most of our users are using our internal search the same way, right? So they were looking for a specific named account. They were not really looking to get to a particular call transcript based on what they thought would be in the transcript, right? They were just looking to get to calls for a particular account. That's how they were using the product. We couldn't rely on those logs. So we had to generate our own data set for search or for similarity. So what we did was we said, okay, let's take calls, let's work backwards, let's identify questions, let's ask a prompt, what questions can this call answer, right? That's how we carefully built a reasonably large search data set, right? So our data looked like this. You have a query, and I'll give you the list of possible answers from this entire repository. You need to be very careful while doing this. So because how do you build the right data set for this? You have given a query, you have to score every single item in your repository to be able to get the truth data for this, right? Most people can't do that. So the next best alternative is to retrieve using some index and then manually score those things, and that's how you build your truth data. But lexical bias has already crept in, right? So things that did not share words would not be retrieved by your system. So you wouldn't know if there is something left in your repository that could have been a good match. We still try to avoid this. We try to. This is probably one of the greatest benefits of LLMs today. We can really scale up our data collection efforts today, right? And the other data set for similarity, we built a data set of clusters. We took a lot of turns and calls, and we clustered them together and said, now I know a truth data for how I would segment my data, right? And the last part is metric. Metric is tied at the hip to whatever algorithm you're using, whatever task you're using, because if it's not a binary task, you can't really use some of these metrics. Like accuracy is basically saying how often when they were similar did you say otherwise, right? That's accuracy. Reciprocal rank is usually an NDCG are both retrieval metrics to see how well you did as a ranking function, right? So what was supposed to be in first place, if you put it in fifth place, I have a mathematical function which accounts for it, and it gives you a clean score that you can use to compare across different runs, right? A clean interpretable score, if I might say. Recall is again saying, am I just retrieving the right documents, right? So there are many metrics. I will pick the most interpretable one to show you today. So for each of architecture, task, data set, I gave you two different options, right? So for I gave you two architectures. One is a projection, one is fine-tuning the entire thing. For task, I gave you two things. One is clustering, one is similarity, right? So I'm not going to do cross product of all approaches. I'm going to show you two setups. 1, 2, right? The first setup is search, retrieval. I have a few thousand query document pairs that I picked up as I showed you. I used embeddings from OpenAI. The architecture is the projection method. That's the first of those two things. And I use cosine similarity to score. And I actually also generated some very hard negatives, very hard for a system to say that this document does not match this query, right? So I generated some things like that. The second setup, I had a few truth data clustering. I picked two random samples. Did I pick them from the same cluster, or did I not pick them from the same cluster? That's the task at hand, right? So I generated two different data sets, and I said, now the question is, I'm going to compare these embeddings, the raw embeddings, vanilla embeddings, and see how well they do. And what if I fine-tune them? How well do they do, right? So this is the first experiment. This is search retrieval. So you can ignore one of them, right? You can just look at the top two or the bottom two. One is the train, one is the test. Okay. Yeah, one is the train, one is test. The top one is test. Probably it's best to look at the top one. What this is saying is the ones in orange, right? That's on the x-axis is what the cosine similarity score was. On the y-axis is a count of how many of those had the same cosine similarity, right? The orange ones are the ones which are not supposed to be retrieved pairs. That is, they are wrong, which means that the orange ones need to be closer to 0, right? They need to be well separate. They need the cosine similarity should say that, hey, this was not supposed to be a retrieved document for a query, which means that the cosine similarity should be low. And the blue ones are, this was supposed to be, according to truth data, this was supposed to be a relevant document given the query, right? As you can see, they're already well separated. Now, why so? Because if you don't include hard negatives, you can just look at if the query and the document share any words and quickly say if if they are relevant or not, right? So which is why the vanilla embeddings were also able to say that very easily. So we said, okay, let's take some negatives which the embeddings are having a hard time saying that, right? Now this is that the hard data set. If you see again on the left is before fine tuning, right is after fine tuning. So in the previous case, before and after fine tuning, you never saw any difference. In the after case, before fine tuning, you were doing a 67%. You're able to split it by that much, right? Remember, this is there were equal number of yes or no, so random sampling will be a 50%, right? 67 is not a great performance. But after fine tuning, you're able to get to 92.5% accuracy using the projection method. And all you're learning is a few thousand parameters, right? To be able to do this. Then this is the second approach, right? Where we are actually, this is the second setup. So to refresh, this is the second setup where I'm actually taking a few truth clusters, sampling a few elements from each cluster and asking the model, are these from the same cluster or not, right? But this time, I'm not just learning a projection, but I'm actually fine-tuning the entire model all the way to the end. And it's the same thing here. If you see, again, this was very hard to answer. Before it was not able to separate this, but we picked but of course it could be because fine tuning is a very hard task. We couldn't really fine tune any of the really large models, so maybe the original embeddings themselves were not very good to start with. But as you use, but you can quickly get a very small model to become very, very performant. As you can see in the bottom graph, clear separation. All the ones which are negative are showing a low cosine score. The distribution is clearly separated from the blue one, right? That's basically what the point I'm trying to make is that this is something that you can achieve with very little data that you can collect in-house and get open source LLMs or even closed source ones. Those are the two approaches I showed you to work for your use case, right? So that's the work. It was super interesting to do this, but it still leaves a lot of scope for future work. For example, I know that in the search use case, I could have encoded the query and the document very differently. I know that each embedding can capture flavors, so you could have multi-flavored one. You could also use some very proven techniques like Colbert, which will look at words individually, which will incur a lot of indexing complexity, but great search performance, right? And also avoid some other problems with embeddings in terms of upgrades and all of that. But there's a lot of, if this is the way it goes, fundamental platform teams, like the ones that Clary has in Poland, they are faced with really hard problems, right? These are big models that you'll need to deploy for on a customer by customer basis, right? How do you get efficient with this? How do you not cause a climate crisis? I mean, there's a great opening talk today morning talking about how we as developers can be more conscious about how the footprint that we are adding, right? So these are some fundamental challenges that in the platform teams need to solve. I think that brings us to the end. I've left about 10 minutes for questions, but I just need to deliver one message. So Clary is opening a new office, has opened a new office. The inauguration is today. You all are invited to it. Please consider this an invitation. And yeah, we have a booth outside. Please join us there, and happy to take any questions. Okay. So how do you deal with typos with the text before embedding? Most typos, all of these are caught somewhere in the tokenization, right? So we don't correct for any of these. Because until I read this thing, I don't even know it's a typo. It's best left to the really large language models, which have seen all kinds of errors before. And even the tokenization, when tokenization algorithms, when they're learned, they would have seen all these before. So usually you don't see word typos because we are dealing with transcripts. You'll see grammatical typos. That's where customization matters to us. We could actually fine-tune the language models to be able to handle and see and handle these kind of typos. So my answer is that it works. That's how we are using it. So text embedding adder 002 is legacy. What are you planning to upgrade to? Yes, it is legacy. That work is from close to 7-8 months ago. The newer work is fine-tuning the entire model. At some point, we will see what kind of performance benefit we get from the newer embeddings. But the newer work is actually fine-tuning the entire model. So how do you host and then access your fine-tuned embedding models? At some point, we were running on SageMaker to host them. We run a lot of these models, so we have cost concerns. We run on Kubernetes, so we were hosting Kubernetes clusters with GPUs and managing all of this ourselves, paying close attention to utilization. That's basically how we host and run these today. Cool. I think that was the end of it. Thank you, everyone.